Thank you for your interest in the Berkeley Microfabrication Laboratory. In this presentation, we will attempt to tell you something about our lab, when and how it started, what's in it, and how it's run. Let's start with a bit of history. In 1960, soon after the invention of the integrated circuit, planning for construction of the world's first university microelectronics and microfabrication research lab began. This new 1,200 square foot facility started producing working integrated circuits on 3/4-inch diameter silicon wafers in 1962. The trend toward further integration through the 60s and into the 70s made clear the need for more sophisticated equipment and an ultra-clean work area. Thus, in 1979, planning for renovation and expansion of the existing facility began. Construction of the new 10,000 square foot Class 100 microfabrication research laboratory began in 1982 and was completed in 1983. Funding for the new laboratory was obtained from the state of California, industry, federal agencies, and the regents of the University of California. The total cost was $4.57 million. The lab's design features modular interior walls, benches, and air handling units to facilitate the frequent changes required in a research environment. The utilities are isolated from work areas and brought in from overhead. The microlab contains everything necessary to design, fabricate, and assemble an integrated circuit. Computer workstations with graphics capability, mask-making equipment, photolithography equipment, an ion implanter, thin film systems, high-temperature and LPCVD furnaces, and a variety of analytical instruments. IC testing is carried out in the well-equipped device characterization laboratory adjacent to the microlab. Much of the microlab's operation is overseen by specially designed computer software. This software not only controls and monitors equipment usage and maintenance, but also handles administrative accounting and provides many convenient data retrieval functions. Research in the microlab is wide-ranging, and though the majority of work being done is related to microelectronics, it is by no means confined to that field. Microfabrication techniques and equipment lend themselves to a wide variety of research endeavors. While 70% of the students using the microlab are affiliated with the electrical engineering and computer science department, the remaining 30% come from the departments of physics, mechanical engineering, material science and mineral engineering, bioengineering, chemistry, and chemical engineering. Microelectronics research in the microlab can be broken down into three main categories: silicon, 3,5 compounds, and superconductors. Of these, silicon represents the largest research endeavor and includes the areas of integrated circuits and systems, technology innovation, device physics, and integrated sensors and actuators. There is a very large variety of equipment in the microlab available to students in all groups. We currently maintain 125 operative systems, too many to show here. Instead, we'll follow a general silicon microfabrication process and show the equipment used. The logical starting point is mask making. Virtually all microfabrication projects require at least one mask, as it is the means by which the desired pattern for any device is transferred to the silicon. Mask making begins with the device design being laid out on one of the lab's 4 computer graphics workstations. Once this layout is complete, it is transferred to magnetic tape and brought into the lab. The red rooms house our mask shop, where the mask plates are exposed and developed. The magnetic tape on which the mask pattern is encoded is loaded into the GCA-MAN optical pattern generator, which exposes mask plates as dictated by the tape. Once exposed, the plate is developed in one of the 2 APT automatic developing systems. One system is set up to develop chrome and iron oxide masks, the other, emulsion. Once the masks are done, actual processing can begin. A process usually starts with a high temperature step, such as oxidation. These are carried out in the Thailand furnaces, which are controlled by a computer called the TICOM. Students use the TICOM to write programs, or recipes, onto floppy disks specifying temperatures, gases and their flow rates, and duration time for individual steps. The TICOM will also read out continuous data on the status of each tube. Processes carried out in the Thailand furnaces include wet and dry oxidation, anneal, diffusion doping, low-pressure chemical vapor deposition, and sintering. The wafer is now ready to be patterned using the mask set generated earlier and the photolithographic equipment located in the yellow rooms. For photoresist coating, there is the Eaton wafer track. This is an automatic cassette-to-cassette delivery system which dispenses photoresist onto 4-inch wafers, spins, soft bakes, and cools them according to parameters programmed into the system by the user. Once coated, wafers are exposed in the GCA MAN wafer stepper, a computer-controlled 10x reduction alignment system. Specifications for a particular job, such as focus, exposure, alignment mark offsets, and array configuration, are programmed into the system. The wafers are then run through the system automatically, though alignment of each wafer must be done manually. The exposed wafers can be developed in one of two ways: automatically in the MTI OmniChuck, or by hand in one of the wet process stations, which will be described shortly. The OmniChuck is set up to automatically develop, rinse, and dry the wafer according to parameters programmed in by the operator. Once the wafers have been hard-baked, the substrate or film underneath the patterned photoresist is ready to be either etched or doped. Chemical etching is done in one of the wet process stations. Each of these is equipped with 2 heated baths, 2 chemical tanks, 6 rinse tanks, a spray hose, and a utility sink. 5 of the lab's 12 sinks have been dedicated to particular processes, and their baths filled accordingly with specific chemicals. This is a wafer cleaning station, which contains 2 baths of hot sulfuric acid, to which hydrogen peroxide is added to make Piranha, a standard wafer cleaning agent. In addition to chemical etchants, we have several dry or plasma etching systems. Among these are 2 lam etchers, one of which is dedicated to silicon dioxide etching and the other to polysilicon etching. For dry etching of silicon nitride, we have the Technique's plasma etcher, which doubles as a photoresist descum ashing system. The Technique's microstripper is used to remove photoresist that is especially tenacious due to heavy implantation or prolonged exposure to plasma. Doping may be done either in the diffusion furnace or by the lab's ion implanter, which can implant a variety of species such as boron, phosphorus, and arsenic at energies up to 200 keV. Other species are available for special applications. When a student requires an implant, he submits a request to the implanter operator, a part-time staff member, who will implant the wafers with the desired species at the specified dose and energy. Once the wafers have been etched and/or doped, they are cleaned of photoresist and go on for deposition or growth of another thin film. Among our many thin film systems are 5 LPCVD furnaces for the deposition of silicon nitride, epitaxial silicon, polycrystalline silicon, and low-temperature silicon dioxide. The CPA metal sputterer is capable of depositing 3 different metals, individually or in sequence. Targets currently in the system are aluminum 2% silicon, tungsten, and titanium, but these can be changed to meet student requirements. Wafers, placed on pallets which stack in one of the 2 load locks on either end of the system, are carried through the machine on a track under the targets to the opposite load lock. Finally, a wide variety of analytical instruments allow students to monitor each step of their process. The NanoSpec AFT employs a computer-controlled microspectrophotometer to measure the thickness of various films. The Gertner ellipsometer measures refractive index and thickness of nitride and oxide films by analyzing the rotation of polarized laser light reflected off the film surface. Sheet resistivity is measured using a Prometrics OmniMap, a computer-controlled 4-point probe, which automatically makes a series of measurements at designated sites across a wafer surface. The computer can store and statistically analyze the collected data for trends, as well as print out maps of the wafer surface, showing the relative resistivity values measured across it. Also available for sheet and bulk resistivity measurements are a simple 4-point probe and the semi-automatic 10-core sonogauge. Step heights are measured on the 10-core Alpha Step 200, an automated programmable profiler with video display and printer. Line widths are measured using the Vickers image shearing microscope. IV and CV probe stations are available for quick checks of circuit devices. For sample inspection, there are a number of microscopes located conveniently throughout the lab. One of these is connected to a color